In this video, we're going to solve our limits using the squeezing theorem. This will be a special limits that no other method or test help us to solve them. Let's say, for example, things like this. We want to understand limit of n reaches infinity of sine of n divided by n. If we plug infinity into n, we get sine of infinity divided by infinity. Sine of infinity, or any sine or cosine, never mind, it's a bounded function. Bounded sequence, sorry. They're bounded somewhere between 1 and minus 1. Their upper bound is 1 and the lower bound is minus 1. If you remember, they actually look something like this. This is the sine, it fits itself, and this is the cosine, starting from here. And it goes like this. It's actually a sine that moved in 90 degrees, but never mind. This is how sine and cosine looks. It's 1 and the upper point is minus 1. We can solve this by intuition. We know that sine 1, sine of any number, is a finite number. So it can be any finite number divided by infinity. It will be 0. And we're done. This is also a good solution. If you explain why I did this, because sine is bounded and it's like finite number, and it's finite number divided by infinity, it's 0. But how can I do this mathematically using squeezing theorem? We know that, what is squeezing theorem? Squeezing theorem says that if we have a sequence an that's smaller or equal another sequence bn, but bigger or equal to another sequence. What does it mean? It means that bn, from some point, all bn numbers are bigger than in an. It can be like, an it's 1 divided by n, bn can be 2 divided by n, and cn can be half divided by n. This is the meaning. If we apply limit to those two sequences, and those both limits reaches L, it means that an also reaches the same limit. Again, what does it mean? If I want to understand what is the limit of an, I can bound it, squeeze it, or make it some sort of a sandwich. It's also called a sandwich theorem. To bound it with other two series, one is bigger and other is smaller. They both reaches the same limit. It means that my sequence will reach the same limit too. It's like if I'm bigger than 5 and also I'm smaller than, if I big or equal to some number, and also I'm smaller and equal to that number, the only option that left is that I'm equal to that number. So this is the squeezing theorem, and how can we apply it here? We can say that sine n divided by n is definitely smaller than 1 divided by n, because sine n is smaller than 1 in most of its points. Sine n is somewhere bounded between n and minus n, between 1 and minus 1, and sine n definitely in most of its points smaller than 1. But it also bigger than minus 1 divided by n. If we apply our limit to those two sequences both reaches 0. So this sequence also goes to 0. It's a very important theorem. You may find that in your, in your homeworks, your lecturer gives you some weird proofs, and you break your head how to do them. And many of the times, the answer is just use squeezing theorem. Let's look at another sequence. So we prove here that the limit is 0. Of course, we can prove it in this way, but squeezing theorem is a more mathematical way. Let's look at the following example of limit of n goes to infinity of 10 in the power of n divided by 3 in the power of n plus square root of n. Maybe it's possible to do here the ratio test, but I'm trying to show the squeezing theorem. In order to use the squeezing theorem, we'll have to find a sequence that's smaller and bigger than the given one. Of course, this sequence is smaller. It's not smaller or equal. It's smaller than 3 in the power of n. What we're doing here, why? Because we're decreasing the denominator. That means that the fraction is getting bigger. And it's bigger than 10 in the power of n divided by 3n plus n. Why? Because square root of n, of course, smaller than n. And bigger or smaller, if n equals 1, it's equal to each other. I'm increasing the denominator, it means that the fraction is getting smaller. So now I want to solve each of those sequences. Hello. How can I solve them? Of course, I can use here the ratio test. But let's take this one. We can write it as 10 divided by 3 in the power of n. The number here is bigger than 1. It goes to infinity. How to know if my squeezing theorem is good is to find two sequences that bigger and smaller than the original one, but the secret and the most hard way is to make them to be the same limit. Because if this equals to infinity and this goes to, let's say, 0, it says that this limit is somewhere between 0 and infinity. So I hope that this limit is also goes to infinity. I can write it in this way. It's like 3 in the power of 2 in n's. It's like 10 divided by 9 in the power of n. Fortunately, luckily, I don't know how to say this, this is also reaches infinity. So I choose a correct sequences to use a sequence squeezing theorem, so the limit here is also infinity.